Hello, good evening, everyone. I hope that I'm audible. If anyone can confirm.
Yes, madam.
Okay, thank you. We'll wait for 2 more minutes. If anyone wants to join, then we'll start. Okay, so I'll start now. So first of all, welcome to this live interaction for the course Nonlinear Vibrations, NOC24 ME54. And this course is being taught by Professor S.K. Dwivedi from IIT Guwahati. And I am Rashyaditi Ranjan. I am a NPTEL PMRF TA and I am a PMRF scholar at the Department of Mechanical Engineering, IIT Patna. And the reason that I'm taking this course is because my PhD work is related to nonlinear vibrations itself. So I'm working on the nonlinear dynamics and control in case of soft robotics. And this subject is very relevant to my research field. So I hope every one of you has gone through the lectures of week 1 and you have got the basic understanding of nonlinear dynamics. So I'll not be summarizing the sessions of the lectures and I'll just be starting this live interaction by taking on questions. And if in case anyone has any doubt, they can ask anytime. So coming on to the first question. As the question says, for a single degree of freedom system, if omega by omega n is equals to under root 2, then the transmissibility ratio dash with the increase of damping. So first of all, this question is of a linear system for a single degree of freedom system. And the transmissibility ratio essentially comes for the system when its base is not fixed and instead it vibrates or actually gives some displacement with time, because of which the motion of the mass is affected. So for example, if I take the example, let us assume that this is a mass. So this is a mass m and it is connected through a spring and damper on a surface. And this mass shows the motion x with time, while this base is also moving with time as y of correct? So in this case, we define the transmissibility ratio in order to define that how this mass m is going to show motion with time. So if I talk about the practical scenario of this case, so the practical scenario may be wherever motors are used. We know that in case of motors, there is a gear mechanism. So in that gear mechanism, what happens is that it is not always necessary that the gear is ideal. That is, the mass distribution is constant throughout the radius. So what happens is that if at a certain point the mass is more, it is going to produce vibrations. So if it's kept on a floor, it is important to damp out those vibrations so that the vibrations are not felt on the floor. These are basically used in industries. Okay, so for this linear system, if we define epsilon as the damping ratio and omega n as the natural frequency of the system, and omega b, which is the frequency of vibration of yt. We are assuming y of t is equals to capital Y sine of omega b t, correct? So in that case, we know that the transmissibility ratio, apart from that, I guess you people know that its equation of motion will be mx double dot plus c x dot minus y dot plus k x minus y is equals to 0. Correct. Now, if I'm going to use this y of t and then I'm going to find y and y dot and then I'll put it in this equation, what is going to happen? This is going to expand. Okay. So after that, I'll see that there is a differential equation is equals to some uh, values related to sine and cos. So that can be solved in order to get the proper solution. And it will be like in two parts. One is going to be the complementary function and other is going to be the particular integral. Okay. So only the particular integral is going to play the role. Can anyone tell me why? Why complementary function will not play a role with time? Okay, fine. The reason is that the system is damped. A damped system means that the vibration, which is due to the natural frequency of the system, it is going to damp out with time. Only the vibration which are due to the forcing function will remain. Okay. So in that case, the transmissibility ratio is defined as capital X divided by capital Y is equals to under root of, let me just erase it. It will be 1 plus twice of epsilon omega b divided by omega n square whole divided by 1 minus omega b by omega n whole square plus twice of epsilon omega b by omega n whole square. Correct? Any doubts? I guess it is clear to every one of you. Okay. So now the thing is that you people must have seen this in the lecture also, but I've still inserted this image in order to discuss that how the transmissibility ratio changes. So here you can see the graph of the transmissibility, displacement transmissibility ratio x by y with the frequency ratio, which is omega b by omega n. So here you can see that the transmissibility ratio is greater than 1 if the value of frequency ratio, which is omega by omega n, less than under root 2. Transmissibility ratio is always greater than 1 for any value of epsilon, which is the damping ratio, right? And with the decrease of damping ratio, what is happening is the amplitude at resonance is increasing. Okay, at value 1. What is 1? 1 stands for resonance when omega b is equals to omega n. Correct? So as you can see that this is what is happening, and for frequency ratio less than under root 2, with the increase of damping, the amplitude is decreasing. Correct? After that, if you'll consider for omega by omega n greater than under root 2, what's happening? Anyone? Okay, so as you can observe that as the damping value is increasing in this case, when it is increasing, the amplitude also starts increasing. Although what is important to notice is that whether the damping, whatever the effect of damping is, that with the increase of damping, amplitude is increasing, but it is always less than 1. Correct. So for this case, transmissibility ratio is always less than 1. Apart from that, as epsilon increases, comma, the transmissibility ratio increases, isn't it? So this is the case. Now, the thing is that the system that I showed you earlier, which is system, this system. So this system is essentially a model of a vibration damper. Okay, so here the source vibration is modeled as y of t. So this is a typical model of a vibration damper, and that is why it is necessary to study this configuration in order to know that how the system is going to behave. Like in case of vibration damper, if I want to install a vibration damper for a practical application in some factory, wherever I want to avoid the transmissibility of the vibrations induced. So in that case, I use this model. I model the system in terms of a spring mass damper system, and then I try to find out the value wherein the omega should lie so that the vibration is damped out. So as you can see that for any case, if omega by omega n is greater than 2, then transmissibility ratio is less than 1, which means that if our base is vibrating with an amplitude of 1, so in that case, the vibration that is transmitted to the mass is always less than 1. It is being damped out. However, the amount of damping that is happening will depend upon the value of epsilon. Okay. So anyways, omega b by omega n should always be greater than under root 2 in order to use it in a practical application as a vibration isolator. Apart from that, as you can see, as the question says that for a single degree of freedom system, if omega by omega n is equals to under root 2, then the transmissibility ratio dash with the increase of damping. So if in this formula I put omega by, sorry, omega b by omega n is equals to under root 2. What is going to happen? Let us see. Let me insert a blank slide. So in that case, the transmissibility ratio TR is equals to under root of 1 plus twice of epsilon. Omega b by omega n will now become under root 2 whole square divided by 1 minus omega b by omega n under root 2 square 2 whole square plus twice of epsilon under root 2 whole square. So then what will this become? Under root of 1 plus twice of under root 2 epsilon square divided by 1 plus twice of under root 2 epsilon square, which will come out to be 1. So transmissibility ratio turns out to be 1 for omega b by omega n is equals to under root 2. Now what does this mean? What would be the answer to the question asked? the transmissibility ratio dash with the increase of damping? You have four options: increases, decreases, remains the same, becomes zero. So, well, it is evident from the figure as well, as you can see here, that for under root 2, the transmissibility ratio is 1. And from the formula, you can see that in this case, whatever be the damping constant value, it won't matter, right? Be it 1, be it 1000, be it 0, it won't matter. The transmissibility ratio is always going to be 1. Now, what does this physically mean? This physically means that for the source vibration, if the frequency of vibration is under root 2 times that of the natural frequency, which is omega b is equals to under root 2 times the natural frequency, the transmissibility ratio is always going to be the same, irrespective of the damping coefficient epsilon. Correct? So the answer to this question will be remains the same. I hope it is clear. So if there is any doubt, you people can ask. Okay. Now I'll move further. So if you people must have gone through the lectures, you must have known this equation, Rayleigh equation. As Dwivedi sir have discussed about 4 to 5 nonlinear equations, one among them is the Rayleigh equation, okay, whose equation of motion is given in this form, right? So the question is that the Rayleigh equation is given as this. This equation is linear, nonlinear, none of the above. So how do I know whether this equation is linear or nonlinear? Okay, so as discussed in the lecture, there are two ways of knowing that whether a given equation is linear or nonlinear. Okay, basically it has to satisfy the superposition principle, right? In order to know whether the given system is linear or nonlinear, we check it by using the superposition rule. Now the superposition rule is further divided into two parts. Okay, so first one is the homogeneity rule. Now what does the homogeneity rule say? Does anyone of you remember? Okay, so for example, if I have a function f, okay, of time t, which gives a result x of time t. Okay, so the homogeneity principle says that if the input f is written as alpha into f of t, then it would result into alpha into x of t. And if this is satisfied, then it satisfies the homogeneity principle. Correct? Coming on to the second one, which is the additive property. Now, what does the additive property say? Now, as the name suggests, that the additive property is talking about the addition. Addition of what? Addition of two responses. Correct. Like, for example, if for a spring mass system, I apply a force F1, then it shows a displacement of x1. Correct. And then if I apply a force F2, then it shows a displacement of x2. Now, what if I apply a force F1 plus F2? Then it should show a displacement of x1 plus x2. Correct? In order to balance the forces. So in this case also, we do the same thing. Like I took the example of f of t. So let us say that if f1 of t gives x1 of t, and if f2 of t gives x2 of t, then the additive property says that f1 of t plus f2 of t should give us x1 of t plus x2 of t. Now we'll be using this same property in order to know that whether this given equation is linear or nonlinear. Although if you see this equation minutely, you'll get to know whether it's linear or nonlinear. But let us just go with this so as to develop an understanding of how are we able to solve this. Because see, this is a very simple equation where you can predict, where you can see and intuitively you can say that whether it's linear or nonlinear. But if you are given a complex equation, okay, with a very big equation with multiple variables, then what are you going to do then? Then for that case, if we have this concept clear, then that would help us to know whether the equation is linear or nonlinear. So I'll just copy the equation. So the equation is, just a second, u double dot plus omega naught square u minus epsilon u dot minus u dot cube is equals to 0. Correct? Yes. So in in this case, what is going to happen? First, we'll look into the homogeneity property. Okay, so let us assume that this particular function is written as d of u of t. Okay, so if I talk about the first one, which is the homogeneity property. So what does the homogeneity property say? As I said earlier also, that f of t, if it gives x of t, then alpha into f of t should give alpha into x of t. In this case, what should be the ideal case to quantify whether the system is linear or not? So if it is linear, d of alpha of ut should be equal to alpha into d of ut. Okay, so what we'll do, we'll just replace u of t by alpha of ut in the main equation and see what happens. So if I add u alpha into u of t in the place of u double dot, it is going to become alpha u double dot of t. Then here it will be omega naught square alpha u minus epsilon. Now here is the problem. U naught will be replaced by alpha u naught, but here we have u naught cube. So what are we doing? We are essentially replacing u by alpha into u, right? So what is happening is that alpha into u, it is like alpha into u d by dt and this whole square. So what would this result in? This would be alpha u naught cube. So here it will be, sorry, alpha cube u naught cube. Here it will be minus alpha cube u naught cube. So does it satisfy the homogeneity property? See, we can take alpha out of it, isn't it? We can take alpha common and keep it out. But it would still not result in the required form. Alpha square u naught cube. And this term is not equal to d of u of t. So this equation does not satisfy the homogeneity rule. Although it is not satisfying the homogeneity rule, we can say now that it is nonlinear. But we'll see the second rule also in order to have a better understanding. Just insert a blank slide. So the second rule is additive property. Okay, so what are we going to do? We are going to consider two cases. First one, we'll replace u by u1, and second, we are going to replace u by u2, and then we'll add and see whether it satisfies the additive property or not. So first, if we replace u by u1, what is the equation of motion going to be? u1 double dot plus omega naught square u1 dot minus epsilon u1 dot minus u1 dot cube is equals to 0. Correct? See guys, it's an interactive session. I'll really appreciate if you can give your input in whether you are able to understand what I'm trying to say or not, because I'm explaining it at my own pace. So if in any case you have any doubt, please tell. I can repeat whatever I am telling, okay?
Sure, madam.
Okay, thank you. Now, when I replace u by u2, the equation becomes u2 double dot plus omega naught square u2 dot minus epsilon u2 dot minus u2 dot cube. Okay, now if we add it, what is going to happen? It will be u1 plus u2 double dot plus omega naught square u1 dot plus u2 dot minus epsilon u1 dot plus u2 dot and minus u1 dot cube plus u2 dot cube. Okay, so this is our d of u1t plus d of u2t. Now we have to check whether it is equal to d of u1t plus u2t. So if I put this in the main equation, what do I get? I get u1 plus u2. Now see, if the differential operator, if it is applied on this, what is going to happen? It will be like this divided by d2 square by dt square. Correct? Now, since they both are decoupled, so this would result in u1 double dot plus u2 double dot. Correct? Similarly is for the case of the first differential as well, d by dt of u1 plus u2. Okay? Which would give us u1 dot plus u2 dot. Okay. But the problem is with the other case, which is u1, sorry, u dot cube. Here, if I replace it with u1 plus u2, I replace it with u1 plus u2, what is going to happen? It will be u1 dot plus u2. Okay, if I'll take it like this, d by dt of u1 plus u2 cube. This would result in u1 dot plus u2 dot cube. And here is where the issue will come. So from here we'll get that d of u1 of t plus u2 of t would give me u1 double dot plus u2 double dot omega naught square u1 plus u2 minus epsilon u1 dot plus u2 dot, but here it will be u1 dot plus u2 dot whole cube. Now if you compare this equation, let us name it equation number 2 with this equation, which let us call it as equation number 1. So here what we can see on comparing 1 and 2, what do we get? That u1 dot whole cube plus u2 dot whole cube is not at all equal to u1 dot plus u2 dot cube, isn't it? So this shows that this equation does not satisfy the additive property as well. So from this, what can we conclude? Since the given equation does not satisfy the superposition rule, it is non-linear. Correct? So if I come back to this question, the answer to this question would be non-linear. Okay, so it is very important to identify that which of the equation is linear and which of the equation is non-linear. Because see, if you cannot identify, it may happen that you will try to solve a non-linear equation like a linear equation, and that would be really tough, and you'll not be able to get the proper answer. Like for example, since you're plus 12, we have been solving that the equation of a pendulum, right? The equation of a simple pendulum, wherein we have a bob and a string attached to the just a second, attached to a bob, and the bob oscillates. It goes here, it goes there. Correct. So if you people must remember that we used to get the equation of motion, and the equation of motion would have a sine theta in it, isn't it? Theta double dot plus g by L sine theta is equals to 0. Sorry. It would be 0. So if you remember, we used to find the solution to this equation, but we used to have a little assumption over there. We used to assume that theta is very small. So sine theta is nearly equal to theta. Correct? We used to make it a linear equation and then we used to solve it. But that was wrong. Actually, it is not wrong, but it is applicable only for a very small range of theta. It is not wrong, but applicable for a very small range. But in practical application, that is not the case. The bob is not going to oscillate for a very small value. Okay, so it is important to take into consideration sine theta. If you'll notice, I would also suggest that if you can go and practice the superposition rule with this equation, it would make the case clear that why the superposition is required. Now, this is a transcendental function, so that is why in this case also the superposition rule is not going to satisfy, and then you can say that the equation is nonlinear. Okay, now I'll be coming on to the third question. Okay, so you people must have seen this somewhere in the lecture where Sir discussed about soft spring and hard spring, isn't it? So let me first define that what is a linear spring. So a linear spring is a spring which satisfies F is equals to Kx, where K is the stiffness and X is the displacement. Or you can say the spring is extension or compression, any one of it. So the spring force is given as Kx, correct? So what is going to happen if I plot force? If this I consider as X and this I consider as F. If I plot force versus displacement. So how is the curve going to go? It will follow the path like this, isn't it? With the increment of X, F is going to increase and this inclination will depend upon the value of this inclination would depend upon the value of K, which is the stiffness. Correct. Now, if I consider the given equation as F is equals to 10x. And for the time being, I don't consider the 17x cubed term. Okay, so how the plot is going to be? It will vary linearly like this. Okay, so this is how it will go. Like for example, at x is equals to 1, for this linear behavior, the value that I'll get would be, let us say that this is x is equals to 1, the value would be 10, correct? But now there are two deflections from this linear spring, which are named as hard springs and soft springs. Okay, so you must have studied about it in the lecture that one behavior is this and the other behavior is this. Correct. In one case, with the increment of x, the value of f increases and after that it tries to go like this. Okay. While in the other case, the value of x increases, the force increases. It diverges from the linear behavior in the upward direction, while the first case it diverges in the lower direction. Okay, so these are the two cases. Okay, so the first one, which diverges towards the lower end, we call it as the soft spring, and this particular behavior is known as the hard spring. Here there is some, like for example at this value, if I extend it, you see that there is this increment of the spring force. Let us say that this is x. No, let us take some other variable actually. X we have already taken. Let us call it A. Okay. So from the linear behavior, there is some increment from the linear behavior. This increment shows that in case of a hard spring, as x increases, the value of force starts increasing. Okay, it does not go linearly. It starts increasing. Although for a certain value it follows a linear behavior, after that it starts increasing from that of the linear behavior. While in case of soft spring, let me call it as B, there is some decrement in the value. Okay, so from this thought and by using this equation, now I can find out that whether the equation that is given is for a hard spring or a soft spring. How? Let us again take the value at x is equals to 1. For the given equation, we'll have f is equals to 10 plus 17, which would give us 27, correct? Which is an increment from the value which is at the linear spring. Increment in the force as compared to the linear spring. Hence, we can say that it is a hard spring. If instead of plus there would have been minus 17x cube, then that would be a case of a soft spring. Okay, I hope that it is clear to you all. Apart from that, there is also one thing that I would like to mention here. And also, yeah, I also wanted to tell you that this theory that I gave you here, you can also check it by the spring that you get in the tip top pen. It has a spring. Take out the spring and try to compress it. See, initially it will be easy to compress it, but after some time, as its length decreases, it will become somewhat hard to compress it. Okay, you'll not feel that smooth, the application of force and the corresponding displacement. It shows that the spring becomes hard. It is also a hardening spring. Okay. Apart from that, I'll also like to show an example. You people must have been knowing the equation of motion of a forced spring mass and damper system, isn't it? The idealization in the spring mass damper system is that we assume that the spring is linear, isn't it? Kx is equal to F sine omega t. We assume here that the spring is linear. Now I can consider that the spring is nonlinear. And I have two options. First, that I introduce a parameter beta x cube in this equation like this, plus let us say beta x cube is equals to f sine of omega t. Now this beta can be positive and negative, and depending upon whether it is positive or whether it is negative, we can know that. Now this specific equation, we call it as a Duffing oscillator. After introducing the nonlinearity, it is known as the Duffing oscillator or Duffing equation, you can say. So if beta is equals to negative, then it is going to be a soft Duffing oscillator. And if the value of beta is positive, then it is going to be a hard Duffing oscillator. Okay. So I'll come on to the fourth question. So this question, the subharmonic of the frequency 100 Hertz is. So the reason that I'm taking this question is because although there is no mention of harmonics like subharmonic and superharmonic in the lecture till now, but there is a question which is related to it in your assignment. So I'm taking up this question in so that it would help you in solving the assignment question. And this superharmonic, subharmonic topic is going to be covered in the further lectures by Dwivedi sir. Although I'll try to explain you that why these things are coming in a nonlinear equation by some of the mathematical jugglery and taking the example of a Duffing equation. And I'll try that you get an idea. I don't want you to get into the mathematics that much. I'll just tell you the necessary mathematics just in order to give you an idea that why these superharmonic and subharmonic are coming into a nonlinear equation. Apart from that, the proper understanding you'll get when you'll attend the further lectures of Dwivedi sir. Is it fine? So let me just come to the Duffing equation again. So firstly, in case of non-linear system, have you ever listened about the term subharmonic or superharmonic? Okay, can anyone tell me what is a harmonic? No? Okay. So harmonic is basically when the forcing function is equal to the natural frequency of the system. What happens in a linear system? It goes to infinity. We say that the amplitude goes to infinity. But has anyone seen this in practical application? The amplitude of oscillation going to infinity. No one must have seen because that is not possible. And why is it not possible? Anyone? Anyone? Just a guess would also work because of the nonlinearity in the system. See, nonlinearity has its own disadvantages and advantages. Nonlinearity actually stops the system from getting to infinity. And that is a very positive point of nonlinearity. As you people must have seen the washing machines when it used to have two separate compartments, one for washing the clothes and one for draining the clothes. Right. So when you would drain the cloth in the draining uh, tub, you must have seen that if the clothes are not aligned at the center, the washing machine would start vibrating. It would show tremendous vibration, isn't it? But it does not go to infinity. It is going to show vibration, but some vibration because nonlinearity is stopping it from going to there, right? So nonlinearity has its own advantages as well. So let us have this equation. For here, I have taken the case of a nonlinear spring and I have taken the nonlinear part as beta x square. You may take it as beta x cube also, but I have taken it as like this for better understanding of the problem, basically for the subharmonic and superharmonic. So intuitively, how the system is going to behave. For a linear system, what was happening? If I don't consider this, what will happen? The system is going to oscillate with the frequency omega, correct? And the frequency which is due to the initial condition, frequency, I'm saying, sorry, the oscillation which is due to the natural frequency or because of the initial condition. It is going to get damped out because of the presence of the damping. Okay, so now this is a nonlinear system, correct? So I'll just assume that it is oscillating. I'll just assume, simple case, it is showing a periodic oscillation. Okay, so in that case, I'm assuming x as a naught plus a1 cos of lambda t plus b1 sine of lambda t. I have taken a truncated Fourier series. Okay, I can go like a2 cos twice of lambda t and b2 sine twice of lambda t and so on. But I have taken the truncated Fourier series for illustrating the idea. Okay, so if I have considered this as a solution, I can take out the value of x dot, isn't it? I can take it out. And lambda, I'm assuming, see, I'll write it here. It is assumed that the system oscillates with a frequency lambda. Okay, for now I've assumed as lambda. I don't know what the value of lambda is. Okay, I'll use the method of harmonic balance in order to find out. What is harmonic balance? We assume a solution, like we're assuming that the system is behaving periodically like the given equation x. Okay, now what we are going to do, we are going to put this x into the main equation, right, on the left hand side, and then we are going to equate it with the right hand side in order to know that what are the going to be the values of a naught, a1 and b1, so that the system is going to behave in this particular manner. Okay, so x naught will be equal to a is a constant, so its differentiation goes to 0. Then this term is differentiated in order to get the x naught, which will give us sine of lambda t, and differentiating the sine function b1 lambda cos of lambda t. Again differentiating again to get x double dot, we'll get minus a1 lambda square cos of lambda t minus b1 lambda square sine of lambda t. Correct? Apart from that, what else remains? X square, which will be equal to a naught plus a1 cos of lambda t plus b1 sine of lambda t whole square. So by using the formula of a plus b plus c whole square, we can evaluate this, which would give us a naught square plus a1 square cos square lambda t plus b1 square sine square lambda t plus twice of a naught a1 cos lambda t plus twice of a naught b1 sine of lambda t and plus twice of a1 b1 sine of lambda t cos of lambda t. Correct? Now, what should I do? I'll try to convert. What can I do? So here you can see that we have a term of cos square lambda t, we have a term of sine square lambda t, and we have a term of sine lambda t cos lambda t. So we'll use some trigonometric equations, like we know cos square lambda t would give us 1 plus cos of twice of lambda t by 2. Similarly, sine square of lambda t would give us 1 minus cos of twice of lambda t by 2, correct? And the remaining one, which is twice of sine of lambda t into cos of lambda t, would give us anyone? Twice of sine cos b, it will be sine of twice of sine of a plus b, which will be twice of lambda t. plus sine of a minus b, which is 0. So sine of 0 is 0. Correct? So I'll not get into the whole mathematics, but from here, if I use this, and this, okay, what can I do? That I can replace these values into the main equation, which is this equation. Totally, I can replace it. Right. What is going to happen then? The thing is that now this x square is going to get converted in terms of, like, it would become, this x square would become a function of what? A naught is a constant, a1 is a constant, and b1 is a constant, right? So what are the changing values in it? I like not time, apart from time. I want to write it in terms of cos and sine. Then what are those things? It will have sine of lambda t, it will have cos of lambda t, it will have sine of twice of lambda t, and it will have cos of twice of lambda t. Apart from that, all other things are going to be constant values, isn't it? And they are going to be its coefficients. And a constant value which will get added up by a naught and a1 and b1. Right. So if if I'll not get into the mathematical everything, because that is not required as of now, that you'll learn in the further lectures. So now if I use all these equations, which is this equation 1, this equation 2, okay, I'll just name it. I'll name this as equation 1, this as equation 2, this as equation 3, and this as equation 4, which now I have converted into like this. This is also your equation 4. Okay. So what will I get? Just these are just going to be the sum ups of cos of lambda t, sine of lambda t, cos of twice of lambda t, sine of twice of lambda t, and a constant value. Okay, and those coefficients are going to be some algebraic summation, multiplication, or subtraction, everything included of a naught, a1, and b1. So here, as I don't want to solve this, I am just trying to give an idea about subharmonic and superharmonic. So I'll not solve it. I'll just write it in this term. I'll write the equation after putting equation 1, 2, 3, and 4 in the equation of motion. EOM I'm using for the equation of motion. Then what would this become? What would the left hand side? LHS would be equal to, I'm assuming, A naught plus A1 cos of lambda t plus B1 sine of lambda t plus A2 cos of twice of lambda t and plus B2 sine of twice of lambda t. Is it clear to everyone, or does anyone have any doubt in it? I have not explained the whole mathematical form, not gone into the equation, but I've tried explaining what I'm trying to do here. Okay, these A naught, A1, B1, A2, B2 are all going to be a function of A naught, A1, and A2. Small A naught, A1, sorry, A2, nahi, B1. Small A naught, small A1, small B1. They're all going to be a function of all those things. Algebraic, I would say, value. Does anyone have any doubt? Or should I proceed further?
Proceed further, madam.
Okay, fine. So now as we got LHS, now if we do LHS is equals to RHS, what can we see? That now see here our, okay, I'll just write here. That would be better. Our RHS is F sine of omega t, and our LHS has terms like this. So since our RHS has, wait, okay, I have considered cos here, right? So I'll write cos of omega t, correct? So since this LHS has a coefficient of cos lambda t and sine lambda t, okay, but our RHS has cos of omega t, okay. So what does this mean? If I want to equate the LHS and RHS in order to find the value of the coefficients A0, A1, B1, A2, B2, I know that since the RHS does not have any sine term, since RHS does not have any sine term, comma, B1 equals to B2 is equals to 0. Correct? So what are the remaining values? A0 plus A1 cos of lambda t plus A2 into cos twice of lambda t. Now if I want to equate the cos term, what is going to happen? There can be two cases, right? First, when lambda is equals to omega, right? And second, when twice of lambda is equals to omega, right? So this is the case which generally happens in a linear system. And this is the case which is not shown in a linear system but occurs in a nonlinear system. What happens in this case? Like for lambda is equals to omega, the time period would be t naught is equals to 2 pi by omega. Correct. But for this, what is happening? For this, lambda is equals to omega by 2. It means that there may be a presence of an oscillation where the oscillation frequency is omega by 2, where omega is the forcing frequency, right? And in this case, the time period, let us assume it as t, would be equal to 2 pi by omega by 2, which is equals to 4 pi by omega. Sorry, here it will be omega, which I can also write as twice of T naught. Then what is this? This is where comes the concept of superharmonic. What is happening? The time period has doubled itself and the frequency has halved itself. Frequency becomes half of the forcing frequency, right? This is the case of superharmonic. So then what is subharmonic? Opposite of it. In case of subharmonic,
Means, madam, in superharmonic,
yes,
the frequency is going to double, I think.
no, no,
Oh, okay.
no, that is not the
Means,
case. Actually, yeah, I understand what you are trying to say. That happens.
yes.
It used to happen with me as well when I was first learning nonlinear dynamics. Because
Yes.
intuitively it comes like that, na? Super means doubling or
Okay.
increment with some integer. It comes like that. But the thing is that super harmonic and subharmonic are actually defined in terms of the time period instead of omega. Right. When we
Okay.
say superharmonic, now you take it like this. Now, intuitively, you have to always take it like this, that when we are saying superharmonic, it means doubling of the time period. And when we are saying subharmonic, it means halving of the time period. And from that, derive the changes in omega.
Okay, means it is
Don't
the reverse. Means in super harmonic the frequency is half, and in subharmonic the frequency might be double.
Yes, exactly. That is why I
Okay.
told you that intuitively it says so, but it is not the case. That is why
Yes.
remember it like superharmonic, doubling of the time period, subharmonic, halving of the time period. And like this is happening in this case, just in case you people might take it like that superharmonic is always doubling of the time period. That is not the case. Okay, here how factor of 2 is coming. Essentially, if I want to define the super and subharmonic, it would be like this. For superharmonic, omega would be equal to omega divided by n. Okay, where n is going to be an integer. While in case of subharmonic, omega is equals to n time of this. Here also n is going to be an integer. In case of superharmonic, the it time period changes like n into t naught, and in case of subharmonic, time period is going to change like this. Is it clear to everyone? So the
Yes, madam.
answer to this question would be subharmonic means 100 into some integer, and that is satisfied only in the option C. So the answer to this question is option C. Now coming on to question number 5. I guess this answer to this question you people can give it, isn't it? I don't have to solve it, or do I? Anyone? If you people must have seen the lecture, you can answer this. Quasi periodic.
Yes. Wow. Yes, it is quasi periodic. Yes, because omega one, omega two by omega one is root two.
Yes, and so what does root 2 say?
Uh, Frequency ratio.
Hmm. Yes,
It
you are
is.
right. Like if omega 2 by omega 1 is under root 2, so under root 2 is a irrational number.
Yes.
So if the ratio of frequency is an irrational number, then the response is quasi-periodic. Okay.
Okay, madam.
Now coming on to question number 6.
But excuse me, madam.
Yes.
Madam, suppose omega 2 by omega 1 is root 2. For some example, there is one example in our assignment, and in that question, there was the second question where y is equal to 3 cos 2t plus 3 cos 2 root 3t. So in that, the response in the phase. So here the ratio omega 2 by omega 1 is root 3, means it is the irrational number, and the
Hmm.
response is quasi-periodic. But there are the four options are there, like a fixed point response is there, or a circle with single loop, or a circle with two loop, or a torus. So how can we differentiate it, whether it is a single loop, two loop, or a single fixed point or torus response?
Hmm. So you got to know. You know the response, right?
Yes, yes, yes,
So, Dwivedi sir must, yeah, right. As far as I remember, he has explained how by using Excel you can plot the time response and phase plot, isn't it?
yes, yes, yes.
So use that, plot it and
Okay, so
see.
okay, okay.
Okay, that's an assignment question. I cannot discuss it, but I can give you the hint that try to plot it and then you'll get the answer. It's very
Okay,
easy.
madam. Okay, madam. Thank you.
Okay. Now again, I'm coming to a topic which has not been discussed to you till now. Buckling of a beam is which type of bifurcation? Does anyone know what is bifurcation? I think you people have not been taught this till the lecture till now. So that is why I'm taking this so that you people will be able to understand what bifurcation is and it will help you to solve the assignment question. Anyone has any idea what bifurcation is?
No,
Okay.
madam.
What is buckling of beam? This you people must be knowing. No one knows what is buckling of beam.
Yes, madam.
What is it? Okay, let me give
When
you a
axial load
practical
is applied,
example.
then
This is
it
a
will going
scale.
to buckle.
You can see this is a scale. You can do this example on yourself also. Okay, this is a scale. If I apply a load on it like this, it is going to remain straight. But if I try applying more pressure, like if I try applying more pressure on it, it is going to buckle. It is going to bend itself, isn't it? Isn't it bending? This is what buckling of beam means. The beam is going to buckle depending upon the force. There is a formula also which is taught in the strength of materials course that gives the value of the critical load for the buckling of beam. So if the load is greater than that critical load, beam is going to buckle. Okay, so what happens is that the beam is like this initially for a mass m. Okay, now I increase the mass. I make it capital M provided m is greater than small m and it is greater than that of the critical load. What is going to happen? The beam is going to buckle. Either it is going to buckle like this or it is going to buckle like this. Correct? So what is happening? There was one state of the system for small m, one equilibrium point. This is an equilibrium state now. The mass, beam and the surface, they are all in equilibrium. They are all in a static condition. They are all balancing by action and reaction. Correct? There is no motion, there is no acceleration, so it is in a static condition. Now, when I increased the mass to capital M, what has happened? The beam is now buckled. Okay. Now it is again in an equilibrium state, but the difference is that initially the beam was straight, now it has bent. And it can bend in any of the two direction. It can bend like it can have a curve like the first case, or it can have a curve like second case. So what is happening as mass is changing? So as the load is increasing, the first equilibrium state changes into two buckled equilibrium state, isn't it? This is what is happening. So this is what we call bifurcation. With the change of some parameter, the equilibrium state is changing. There was one equilibrium state earlier. Now with the change of parameter, Now there is existence of two equilibrium states, which is different from that of the first one. Okay, so I'm assuming that you people don't know these four types of bifurcations that I have given in the option. So I'll be explaining briefly, not thoroughly, just briefly, because this also you'll learn in the coming lectures. Okay, so first one is the saddle node. So what happens in a saddle node bifurcation is I'll use a equation in order to demonstrate how a saddle node bifurcation is. So the equation of saddle node bifurcation is given as x naught is equals to r plus x square. Okay, so what are the fixed points of this equation? Can anyone tell me what are its fixed points? Okay, in order to calculate the fixed point, what do? We do x naught is equals to 0, which is equals to r plus x square. From here I get x square is equals to minus of r, x is equals to plus minus under root of minus r. This gives me the fixed point, or what we call as the equilibrium point. What is going to happen at the equilibrium point? The velocity is going to be 0, isn't it? The system is going to be in equilibrium. So that concept is used in order to find the fixed point. Okay, so what is going to happen for r? Let us take a case 1, r less than 1. If I plot the x naught versus x, how is it going to be? It is going to be like this, isn't it? Here it is going to have two fixed points. So I don't know whether you people know it or not, but I'll just tell you that in order to know whether these fixed points are stable or unstable, when we say stable or unstable, it means that the system is going to achieve it or whether the system is not going to achieve it. It comes from the concept of, like, you people must have known the stability, this and this. This is a stable equilibrium state and this is an unstable equilibrium state. If I'm going to take this ball and keep it here and then leave it, what is going to happen? It is going to oscillate and come back to this position again. But if I'm going to displace this ball even for a small value, it is just going to go far away from this state. It is never going to come back. So this is a stable equilibrium state point and this is an unstable equilibrium. Okay, so in order to know whether a fixed point is stable or unstable, and in both these cases, forces are going to balance itself, isn't it? It is going to balance itself. So if the plot is above of the x-axis, which means that the velocity is more, right? So what is going to happen? The thing that is going to happen is that if the velocity is more at a point, it is positive. If it is at this point, its velocity is positive. It is going to let it move away from that point. It is going to move away from that point, isn't it? So from this point, it is going to move away. Here, the velocity is negative, which means that it is going to go like this. If the object is here and its velocity is negative, it is going to go in this direction. So here I can make the arrow like this. And here also, you can see again, here the velocity is positive. So what is going to happen? The arrow is going to be like this. So the system is going away from this point. So this is a unstable equilibrium point, and I mark it as a unfilled hole. And this is a stable equilibrium point. Okay, so what is happening is at r less than 1, the system is having a stable equilibrium point and an unstable equilibrium point. Now let me come to case 2. R is equals to 0. I'm taking it like at a much faster pace because I have limited time and I have to discuss MATLAB also with you people. So for r is equals to 0, what is going to happen? there is going to be only one fixed point, which is x is equals to 0, isn't it? Now the question arises is that whether it will be a stable fixed point or an unstable fixed point. Again, here the velocity is positive. So what is going to happen? It is going to take it away. Here again the velocity is positive towards it. Now what is this happening? In one direction it is taking it away, in other direction it is taking it towards the fixed point. So this is a half stable fixed point. It is stable for this half and unstable for the other half. It is a half stable fixed point. Coming on to the third case, if r is greater than, wait, it should be 0, greater than 0. What is going to happen? If r is greater than 0, this becomes undefined, isn't it? This becomes undefined. There is no fixed point. The system is going to be like this. Now this is a saddle node bifurcation. With the change of parameter r, initially there was a set of saddle point and stable node. As r became 0, there was an existence of a half stable fixed point, and as r became greater than 0, the fixed point vanishes. So this is known as the saddle node bifurcation. Now the second option was, second and third are actually subcritical pitchfork and supercritical pitchfork. Okay, so if this is a saddle node bifurcation, is our system buckling of beam obeying this? Anyone? Is buckling of beam a saddle node bifurcation? Is buckling of beam a saddle node bifurcation? Good. It is not. So then let us come to pitchfork bifurcation. Now pitchfork bifurcation is of two types, subcritical and supercritical. So the question arises is that what is the difference between a subcritical and supercritical bifurcation? Isn't it? Or what is even the difference? So now let us talk about it. Again, I'll use the equation in order to explain that how a pitchfork bifurcation is. So actually, why from the name you can get an intuitive feeling that pitchfork, fork, it would have something of a shape of a fork. The bifurcation diagram would look something like this. There would be a pair. Either there would be a pair of two stable equilibrium points, either they both would exist and would go into one stable equilibrium point, or there would be one stable equilibrium point and then with the change of parameter it would go to two stable equilibrium points, or it can happen that there is one stable equilibrium point and with the change of parameter this stable vanishes and there exists two another stable equilibrium unstable equilibrium points. Anyways, there is also always going to be a pair. So let us first take the example of supercritical pitchfork bifurcation. So in this case, the equation x dot is given as rx minus x cube. So again, if I go on plotting, firstly, I'll identify the fixed points. In order to get the fixed points, I'll take x common, r minus x square is equals to 0. So x is equals to 0 is a fixed point, and x square is equals to r, which implies x is equals to plus minus under root of r is going to be another set of fixed point, isn't it? So in that case, now I'll try plotting. So for r less than 0, first case, what is going to happen? For r less than 0, under root r is not defined. So there is only one fixed point, isn't it? Which is 0. So in that case, just a second, like this, x dot. How is it going to behave? It's going to go like this. And this is going to be a stable fixed point, isn't it? Now, when I come to the case r is equals to 0, again, there will be only one fixed point, 0. The only difference in this diagram would be that this would go like this. The inclination would change a bit. And this will again be a stable fixed point. Then comes the third case, which is for r greater than 0. Now this time we have three fixed points. Okay, and the plot will go like something like this. So here the arrow would be like this. Here the arrow will be like this. And this. So what happens now? Now 0 has become a unstable fixed point, and these two value has now become a stable fixed point. So is this the case of the buckling of beam? Anyone? Yes, this is, isn't it? Yes, good. This is the case of the buckling of beam. And so the answer to this question will be supercritical pitchfork bifurcation. Anyways, if I change this to plus, that is x dot is equals to rx plus x cube, then that this would be our subcritical pitchfork bifurcation. And here you'll see that for r less than 0, you're going to have, like in this case, for r less than 0, we were having one stable equilibrium point. In this case, for r less than 0, you'll have three fixed points, but out of those three fixed points, only one is going to be the stable one. The plot is going to be like this, and in this case, these two will become the unstable fixed points, and this will become the stable fixed points. And with the change of r, like this is for r less than 0, for r is equals to 0, it would be like the characteristic of the graph would change, and it will be like this. And this will be your unstable fixed point, isn't it? This will go like this, and this will go like this. And for r greater than 0, only the inclination is going to change a bit like this. And it is again going to be the unstable equilibrium point. isn't it? So initially this system was stable. As the parameter is changing, it is going to have no fixed point. Then what is going to happen? The system will become unstable. It is going to observe somewhat like failure, isn't it? Now coming on to question 7, which among the following materials changes its stiffness with the change of electric field? Now, when I say stiffness, I actually say that it's behavior, or I would say it's potential well, potential, potential well changes. Now, any one of you know about any of the three materials that are given here? Any idea about these materials? Okay, I'll give a brief description. Okay. First one is a dielectric elastomer. So dielectric elastomer is essentially those materials that show deformation on the application of electric field. Okay, they show deformation on application of electric field E. Okay, these are used as active dampers, vibration damping. For the vibration damping purpose, what is going to happen is, see, this system is having a potential. Okay, it will have a limit of compression and it will have a limit of extension. Correct. Now, if I apply electric field, what is going to happen? It is going to show deformation. It is going to show decrement of the length in which the field is applied. So what is going to happen? It is going to change its potential well. Right. It is going to change its potential. It is going to change the way it is going to behave. And hence, it may be used as active vibration dampers. Okay. Second is the shape memory alloy. So shape memory alloys are the materials that have the capability of remembering its shape. Okay, so what is going to happen is, if you are going to change its shape and then you are going to heat it, it is going to again gain back its shape. Okay, so they have the capability to remember their previous shape. And magnetoactive elastomers, in analogy to the dielectric elastomer, is the elastomer that shows deformation in the application of magnetic field. Okay, and about the idea of magnetoactive elastomer, you can get from the MR flutes as well. Like MR flutes are used for the as adaptive dampers in case of automobiles. Likewise, magnetoactive elastomers can also work as adaptive vibration damping. Coming on to question number 8. So the equation of motion of a system is given as this. The system will. Okay. So see, I have less time left with you and I want to tell you about MATLAB, which will help you to solve the assignment problem. So I'll not go deep into this. I have taken this question in order to tell you that how you can use MATLAB for getting out about the system's behavior. So you can see that this is a linear system, but two-dimensional, isn't it? So how will I know that how the system is going to behave? So there comes a concept of eigenvalues and eigenvectors, eigendirections, I would say. So for a two-dimensional system, the eigendirections are essentially those directions wherein we can say that the change of the differential is in the same direction as that of the change of the variable. Like I can write this equation as capital X dot is equals to A into X, where my capital X dot is X dot into Y dot. Capital X is X and Y, sorry, and A is your 3, 4, minus 7, minus 2, isn't it? So if I am able to get out the value of the eigenvalues, I can predict that what the system is going to behave. Okay, and from this you can get the fixed point also. It is going to be 0, comma 0. Yes, so if I want to evaluate its eigenvalue, so the first way is how we solve it. We take A minus lambda I into X is equals to 0. Since X cannot be 0, A minus lambda I, that we use the concept of determinant, and we say that the determinant of A minus lambda I is going to be 0, and then we use it to evaluate the value of the lambda, which is the eigenvalue. Correct. Now the eigenvalues can either be positive, they can be negative, or they can occur as a complex conjugate. So what is going to happen if the eigenvalues are negative? The eigenvalue is negative. So if the eigenvalue is negative, it means that the system is going to behave like if it is at a position here and its eigenvalue is negative. So what is going to happen? This position is, for example, positive and the eigenvalue is negative. It means its velocity is going to be negative. It is going to attract it towards the fixed point. Correct. So what is going to happen? The system is going to converge towards the fixed point. Both, if I say both lambda is negative, system will converge to the fixed point. And if both the lambda is positive, then what is going to happen? The system is going to diverge. Simple. If it is at a positive value, it will go on going to that positive value. It will diverge. But what if the lambda is of the form A plus IB and A minus IB? Now, here are going to be two cases. One when A is less than 0 and another when A is greater than 0. Now, there's one thing that is clear from these definitions, that if the real part is positive, right? Sorry, the real part is positive. The system is going to diverge, but it is having a complex value as well. And the complex value means it is going to oscillate. So how is the system going to behave? System will behave like this. And what if the value is negative? Again, the system would oscillate also, but diminish also. Then the system would behave like this. This is the difference. So, in order to know that what this system is going to behave, if I evaluate the eigenvalues, I can say that what the system is going to behave. So you can use this also. And the second way is using MATLAB for it. Okay, so now I'll just switch to my laptop in order to tell you that how MATLAB we can use. I hope that my screen is visible.
No, madam, still not.
No, but I think my screen is visible. Yes, maybe it must have been some network error on your side. It is it visible now? Okay, I'll just start. So I'll open the PPT here so that it would help. So this is the question, right? So we made a matrix out of it, isn't it? And now we can write it here in MATLAB. How? Let us say it is A is equals to. Uh, I hope that you people know some basics of MATLAB, or if you'll have doubt, please ask me. Okay. So 3 minus 3, 4 minus 7 minus 2. Yes. Now I want to find the eigenvalues. Now what would I do? So there is a command in MATLAB which is EIG of A. So EIG of A essentially gives me the eigenvalue of a matrix A. So the eigenvalues have a negative real part and the eigenvalues are complex conjugate, right? So what is going to be the answer? See, if you have a negative real part, it means it is going to diminish, and you have the complex conjugate, it means it is going to have oscillation, which means that it would spiral in with decreasing amplitude. So option C is the correct answer, isn't it? C is your correct answer. Any doubts? Okay, I'll come to the next question. So you people must have known van der Waals equation from Dwivedi sir's lecture as he mentioned about it. So this is a equation for van der Waals equation, and the question is the response of the system after 10 seconds and initial condition changes from 1 comma 0 to 2.5 comma 1. So first is how are you going to solve this equation? This is a nonlinear equation, correct? So you don't have a closed form solution for this equation. Okay, so in order to know that how this system is going to behave, we solve it numerically. Okay, we use the ODE45 function of MATLAB. The ODE45 is a numerical technique which uses numerical formulas to evaluate the value. Okay, what do we do is that this is a continuous equation, right? We make it a discrete equation. We basically find it in a discrete way, the solution of this equation. Like if I know the initial condition, like at t is equals to 0, I know that the value is going to be 1 comma 0. So at t1, what am I going to do? I'm going to use this value at t is equals to 0 in order to evaluate the value at t is equals to 1. But since this is a nonlinear equation, the variation is not linear. Okay, so that would result in some error. So in that case, what would I do? I would try to make this difference, like first I consider t0 and then I consider t1. There's a difference of 1 second. Okay, I'll try to make it small, maybe 10 to the power minus 4 or 0.01. What would happen then? So curved for a curved behavior, if I take a very small value, I can assume it as a straight line, isn't it? By using the same concept, I'll try to break down these 10 seconds in an interval of 0.01, assuming that the linear variation exists for 0.01. Okay, so if I know the value at t0, I can evaluate at t of 0.01, then I can evaluate at t 0.02, then t 0.043, and likewise I can go till 10 seconds. Okay, so by joining these linear parts, I'll get the full response of the system. Okay, so how should I enter this equation in MATLAB? Right, I have to create a function first in order to enter it into MATLAB. Okay, so I have two things here. One is the first differential of V and second is the second differential. Okay, so I have to put it in MATLAB. Now what does ODE45 do? You give it x dot, the equation of x dot, it is going to evaluate x for you. But here it is V double dot. Then what should I do? So the best approach is to convert second order ordinary differential equation into two first order ODEs. But how am I going to convert it? Very simple. You'll have two equations. First one is the velocity, second one is the acceleration. Okay, you'll have two equations. First one is the V dot and second one is the V double dot. You can write V double dot as, it's like, let us assume that V dot is a variable x. Hmm. Then V double dot will be x dot. It becomes a first order, isn't it? Similar approach is used here. I have defined the function in this form. What have I done? I have defined z dot. First is z2. Z2 is what? I define a variable z. Okay, where z1 is my displacement and z2 is my velocity. Okay, so what am I doing? I'm first integrating z2. If I'm integrating velocity, what I'm getting? Definitely I'm getting the displacement, right? And if I'm integrating the acceleration, I'm getting the velocity, right? So I have basically made z as 2 cross, like, yeah, 2 cross 1 matrix, right? So first is going to be the velocity and second is displacement, and second is going to be the velocity. Now how am I going to get the displacement? By integrating the velocity. So the first part of z dot should be the equation of velocity, which is z2. Then only velocity will get integrated and give us the displacement. And the second part should be acceleration. And how can I get acceleration now? So from here I can write v double dot is equals to, all these terms are going to come to the right hand side. Okay, so then I can write the equation in MATLAB as this: mu into 1 minus z1 square. Z1 is my displacement, v, into z2, where z2 is velocity, minus of z1. Z1 is again displacement. So I have defined z dot. This is what I use function to define. And this is what I'm going to integrate in order to get the displacement and velocity. Second, I have taken mu as 1.5. You can take it as any value. Okay. Then I have taken t. I have defined it in square brackets. 0 is to 0.01 is to 100. Now what does it does? Let me take an example. T is equals to 0 is to 0.01 is to, let me say 1. Or maybe I'll just use 1 is to 10. What did it do? So T is an array now with the value 0 to 10 with a difference of 1. If I take 2 here, in between, then what is going to happen? Then it is going to vary t from 0 to 10 with a difference of 2. So what is happening here? Here t is defined from 0 to 100 with a difference of 0.01. Simple. Then I have defined initial displacement and initial velocity. Now this is an initial value problem. ODE is an initial, can maybe solved by an initial value problem. Okay, in which we have the initial value and then we can evaluate the further time response of the system from that initial value. So the initial value is given here. We take the first case 1, comma 0. So in that case, what is happening? I've given the initial displacement variable as 1, initial velocity as 0. You can take it as anything, AB or anything, ID, IV, that is on you. I have taken it for the explanation as initial underscore displacement is equals to 1 and initial underscore velocity is equals to 0. Now I define Z0, where Z0 is what? Initial condition. This I have defined it as an array again, initial displacement dash, sorry, space, initial velocity. That one again in a square bracket. Okay. Then I have defined options. This you can ignore as of now. We'll just keep it like this. Okay. This OD set and relative tolerance and absolute tolerance, I'll take it over in the further classes. This is not required as of now for simple equations. Okay. Then I have defined t comma z. There are two things that I'm getting after integration. One is t and another one is z. Z is our variable, which includes the velocity and displacement both. Then I have applied ODE45. Now what is ODE45? Now that I would like to explain you with doc ODE45. Now this doc space the function. Okay, it is going to give you the explanation about what is this function in MATLAB. In case you have any problem regarding any of the function or how to use it, how to give the input, how to name the variable of the output, what are the variables that we are getting as an output, you can go it like this. Here you can see that you will get the proper explanation along with the example of how any function may be used. Okay, so here you can find the explanation. However, I have tried explaining how OD45 works. It basically works on a numerical integration technique in order to solve the ordinary differential equation. Okay, so this is how you give the input to an ODE45 function. We write ODE45 at the rate t comma y. If you define the function inside ODE45, then this is required. Otherwise, you can just call the function. Like in my case, I have defined the function at the end of the file and I have called it. Okay. Comma t-span. T-span is essentially the time that I'm considering for integration, and y naught, where y naught is the initial condition. So I have called at the rate ODE fun t comma z naught options, which you can leave also because we have not defined, and comma mu, because mu is a variable that I'm taking and I'm defining it above. If I would have used 1.5 here instead of mu, then I can just remove here from the OD45 command. And I've used figure 1 and figure 2, which says plot t comma z is 2 comma 1. Like the colon here means all the values corresponding to the first row. Like see, if I will show you like z, if I'll call z, z is like this. Okay, so it has three columns and multiple rows. Okay, so z of colon comma 1, actually what does it does? It takes all the values of the row of the first column. If it is colon comma 2, it is going to take all the values of the column 2, and if it is comma 3, then all the values of third. Okay, so I'll just run this, see what the result comes. Okay, there was an error. But there is an error with MATLAB. So I'll just change this variable as tspan, and then I'll call it here as tspan. What is the problem? It is not integrating, right? Maybe I'll just run this first. Let's see what's happening with this. Okay, it is giving the right value, correct? So this is just for a single differential, like if I consider only a first order differential equation. So this is a code for that, and it is not having any problem. But here there is some problem which we are encountering. Just try to use this equation here, and I'll just put mu as 1.5. I'll just make it 0, and I'll make it 1. I'll see what happens. Now it is giving the right plot, right? Just use this command here. I'll have the solution. Okay, so figure 2 is the phase plot. Okay, figure 2 is the phase plot, and figure 1 is the time response. So here you can see that for 1 comma 0 the response is like this. Okay, so now as the question says that the response of the system after 10 seconds as initial condition changes from 1 comma 0 to 2.5 comma 1. So what am I going to do? I'm just going to change the initial conditions here. It will be 2.5 and it will be 1. I'll just simulate the system, and I'll see that there is some initial difference, and after that the time response and phase plot are the same. And this is where the concept of limit cycle comes from. Okay, so essentially the van der Pol equation has a limit cycle. In this equation it may be seen that this is the van der Pol equation and it has a limit cycle for this value of mu, and that is why with the change of parameter, initial condition, it is again reaching the same phase plot. And so the answer to this question will be remains the same. Okay, so I guess that is it for today's live session. So if you people have any questions, you may ask. I mean, the concept that I used for the van der Pol equation, same can be used for any other type of equation. The only difference that would be needed would be like for a if there are three equations, right? Three-dimensional system. And in that case, you'll use, like here for this system, I have used Z1 and Z2, right? In that case, you can use like that. The number would start increasing. And then you will have to, like, if there is a three-dimensional equation, like you have defined x dot, y dot, and z dot, then in that case you'll have to give three values here, like three equations, three function, like three inputs here as a function, which it will integrate with time, which would be the equation of, oh, who is, okay, so which would be the equation which may be used, like for example I have this example of function which is for the Lorentz equation. Herein I have introduced three derivatives x dot, y dot, and z dot, which is integrated with time. Yeah, so there are three inputs to the z1, z2, and z3. Okay, so what is going to happen is I'll give the expression like this, and then I would use the same way like I did for the Lorentz equation. The changes would be, first would be that in the function, and second would be that in the initial displacement. Like it would be a array with three values. For Wonderpore, it was two values. Okay, you'll have to define the values here. Okay, you can either use it in the function also, like this. Like this is the response of a Lorentz system, this is the time response, and this is the phase plot. Okay, so I guess these questions would help you solve the assignment problem. And if there is any doubt, you can ask me now also, or you can ask in the next class also. That is also fine with me. Anything anyone has to say, or we can just conclude this live session. I guess no one has doubts. So I'll end this meeting now.
Thank you.